morning, everyone. I am Rajath, and I work as a data scientist. And I'm going to talk a bit about designing sustainable, future-ready machine learning data models, and how do we sort of build a bridge between data scientists and fellow data engineers, and try to build better, efficient, compute-friendly models. And simple solutions and techniques that I've incorporated in my career that has helped me put the maximum impact as well. So a bit about where I work. I work for an electricity distribution company. It's United Energy, City Power, and Power. And there's electricity generated, and then we are responsible to distribute this electricity across homes and businesses across Victoria. And we operate, Power basically operates on Western Victoria, consisting mostly 64% of the landscape. And City Power is predominantly on Melbourne City and inner suburbs. And United Energy operates on southeastern suburbs and Peninsula region. And our network can get as complicated as a house that's an individual small house. It could be an apartment and a house having a huge solar panel, or it could be as complex as a huge battery or electric vehicles and stuff around it, right? So we are responsible to deliver electricity which is affordable, reliable, and safe for your homes and businesses. So today's agenda, I'm going to walk you through fundamentals of machine learning architecture. And I'm going to run you through a use case that I'm currently working on. And I'm going to walk you through the learning journeys that I've sort of learned over the period of time. And I'm going to leave you with some takeaways. Let's talk a bit about what's happening in AI space, right? So we started off with statistics and analytics that's influencing our decisions on day-to-day basis, and it moved on to intelligence that sort of makes its own decisions as well. You can take an example of VAR systems or Hawkeye in sports and self-driving cars and whatnot, right? And this is sort of sparked an interest within the data science community to build more models which can interact between themselves to address a complex business need. And so the whole talk is about how do we ensure we have learned small little techniques that we already know of can be implemented that can make our models efficient and compute friendly. So this is a simple ML architecture. It starts off with understanding the use case. Understanding the use case and problem statement is what helps you tailor your solutions as well. And the first phase is data exploration and collection. And in this is where we work with data engineers to gather the data, try to ensure that this data is useful, and we can sort of identify patterns, characteristics, and features from this data. And this is, again, engineered for a better use that can be inputted or trained a model on. And that's where the feature engineering starts. We build a model, we deploy the model, and we try to monitor how the model is performing over time, which is kind of neglected sort of domain at the moment in this current market scenario. But that's another thing that I'm going to talk about as well. How do we use simple practices that's out there that can, like, when you sort of club all of these together in a right way, you can sort of build a better model. So before getting into the slide, so this is electric vehicle detection is something that I'm currently working on. And why do we need to detect electric vehicles is kind of redefined the way we as consumers use electricity on a daily basis. and the load is huge. And it's not as simple as new gadget coming in or PS4s or new technology, right? In this, the stakes with respect to electricity is huge. It is given similar or a bigger impact than solar per se, right? So why do we need to identify electric vehicles within the network? Just imagine a house or a street with 10 houses that's been supplied by a transformer. The electricity is supplied by a transformer, and about 6 of them or 5 of them have electric vehicles, and they get back from work and they plug in their electric EVs to around the same time. That's going to spike up the consumption, and around the area, the aggregated amount would spike up. So we are responsible for all the assets, right? So the transformers, poles, everything. So our assets might not be able to withstand that much of consumption or load on it. So how do we better manage or prepare our network so we can upgrade our assets within the network, so we can prepare where the growth trends are higher, and then we can sort of plan our network and capacity accordingly. So that takes us to the high-level use case, where we started off with understanding what sort of model and how do we model this out on machine learning. So we started using consumption. We looked at voltage and current, but then we settled with consumption profiles, which was giving us a better sort of a data to look at and explore more. And the second one is how do we get granular enough, but also be able to compute the whole network, since it's almost the size of Victoria. That's a lot of data points. So we get data from smart meters from every single house. It's a real-time data as well. So we capture that. How do we kind of process this across the network and try to detect EVs? So we came to a consensus that monthly record or snapshots of where these EVs are collected or accumulated within the areas can be detected so that we could plan accordingly. So the granularity that we went for is on a customer level using the consumption profile and on a monthly scheduled run cycle, right? So this sort of benefits the business in many other ways, where there's a whole team of people who are working on managing the assets, on approving new customer connections, and they're sort of planning the demand and forecast as well. Forecast of what could be the demand for this particular area. Where in Victoria is the landscape growing or residential properties growing? And then how do we ensure that we sort of meet our KPIs with respect to delivering electricity? So that brings us to the exploration phase. We went ahead to understand how a typical electric vehicle charges and what does it look like with respect to consumption. On the graph that you see out there, the blue line indicates the continuous blue line indicates the consumption. On the y-axis is the consumption, x-axis is the time. And onto your left, onto the right, you see a single charge, and that's how it looks like. The amplitude can vary anywhere between 4 and 16. It's not the same because there are different models, different charging stats, and different chargers, in fact, with different ratings. So that changes, and the duration also changes from 1 hour, half an hour, to up until 8 hours or 9 hours, right? And when the same customer over a period of 4 weeks looks like this, with a few peaks, and you can easily notice that how many times an EV is charged in a month, right? And this sort of was our initial understanding of how we go about building an AI or machine learning model. And then we tried to extract features out of this. So we saw the graph, and then we were like, okay, this is easy peasy. We get the peaks and the duration and whatnot. We get these sort of extract the features and characteristics from this, and we sort of reduce the 4-week worth of consumption time series data into a single column, single row per customer. with all the stats and data points that can be fed into the model. So this was computationally very expensive because just imagine 4 weeks of data for each customers across Victoria being reduced to one single row with what information that we want is captured in those features as well. And then we built a model, we decided on a binary classifier, and we built it and deployed it as well. And for today's analogy, I'm going to use Spider-Man as sort of a reference for a model, right? You'll soon know why. And our first version of the model was deployed, and there we have the first Spider-Man as well. Yep, here, with every superhero movie or comic, the superheroes are usually challenged, and this sort of pushes their boundaries as well. In this case, our Spider-Man 1 was kind of naive. It was picking up hot water load. Electric hot waters are, it's the hot water systems that is installed in your houses. It was picking them up, and it was just telling us that this looks like an EV, but it's just frequently charging, which is surely not the case, because even they have a similar amplitude, and they charge for 2 hours, 4 hours, depending on the water usage as well. It's similar, sort of makes sense that the model is doing this. So we went ahead, we built a couple of other features, we tried to tweak the model, and we deployed our Spider-Man 2. And yet again, we found another sort of an outlier or an edge case. This time around, it was heating and cooling effect. So we were scratching our head. I'm like, what sort of load is it? This doesn't look like EV, but our model is picking it up. Then when we overlaid our temperature profiles of the particular customer onto the graph, we got to know that whenever there's an increase in the temperature, the consumption increases as well. And we sort of noticed in other customers with a cooling load as well. This could be a huge aircon that's turned on for a day or whatever, or it could be a floor heating, and so many of these sort. So we got in temperature data, weather data, and we tried to build in a couple of other features, and we deployed our Spider-Man 3. We thought that was robust, and we were like, okay, this is resilient. Let's go with the Spider-Man 3, and this would be our final one. But nope, we hit another roadblock, another sort of an edge case where this was not a lot, but what we found out was there was a lot of EVs picked up on the peninsula region. Mount Martha, Rye, and all of these. I'm like, why? Okay, I do understand that there are a lot of people and they could afford electric vehicles, but when we took a deeper look at few of these cases at Peninsula, not all of them, but few of these cases, it looked like this. And it was not correlating with the temperature graph, temperature plot, but there was consumption on few days, well, the whole week or few other days, there was no consumption at all. These consumptions were correlating with weekends, holidays, but it was kind of mix and match as well. This got a bit more trickier. And we sort of figured how to deal with this, and we fixed it with few other features, and tweaking the model, and we have deployed the amazing Spider-Man, and at the moment, it's running on our prod and keeping our hopes high, I guess. Hopefully, this is the most resilient that we have gotten, and why I sort of took you through a journey of what a data scientist would do on a day-to-day life or a project basis is to let you know that it's not you have a problem statement and you know what to do, you fix it. No, machine learning can get tricky, and this always happens in cycles. And we work on different models, different versions of them, or we use different techniques like champion challenger. If champion can be productionized, there would be similar other models with different parameters that would challenge the champion and make sure they perform well to be deserving to be deployed on prod. We have so many of these techniques, right? So this sort of working on these sort of data science projects sort of got me in questioning about these things. like how do I demonstrate continuous improvement without affecting the regular business flow, right? So this is what I was talking about, the challenger champion model, where you only, even though you are experimenting on a lot of models, you don't productionize it until and unless you are very sure of it. And the second question is, how do you compare these models? Yes, it is easy for us to do it. We do it on a day-to-day life, and we like to compare these models and understand what the advantages are, disadvantages are, and how do we ensure that we give the right predictions as well. But is there a way to automate these predictions? This is one step higher than just comparing it manually. But okay, why do we have to do this? Because in future we are going to work on different models. It could be like in conjunction. So at the moment we have recommendation engine and there's classifier engines on Spotify or Google or these pioneers, right? So they work on different models, and these models try to coordinate with each other, interact with each other to sort of solve a complex business use case. And that's where automating model comparison and trying to promote the right one to the prod or the workflow matters. Second, the third one is how do we optimize compute? Why optimize compute is, in my experience, I've seen a lot of data scientists who have very less understanding on why do we need to optimize queries. We just have a data, we just have a model, we try to build them. Like that's okay if you're building a small sort of a project or with a smaller data set. But with the data that we have, about 50 TBs of data every week coming in and whatnot, it's increasing. And when you take like a lot of time or to compute, and this sort of reduces the number of use cases that we can compute, or it's going to put up our operational costs. How do we optimize it? And how do we sort of find solutions for all the above questions that are future ready and sustainable as well? So it's not just tactical solutions, it's how do we find strategical solutions that can, the small little tweaks that we can perform or we can work with people to get there. So it's sort of sustainable, and we are ready for the future as well. So that brings us to my first learning about ensemble learning. So ensemble learning is a technique where we've started to use multiple models to cater to a complex business use case. One could just complement the other, or one model could feed into another model, and so forth and so on. So the sequential ensemble is when you want more accuracy and less precision, and there's so many model comparisons and the way we sort of consolidate these results and whatnot, right? So we have forgotten, or we limit our use of ensembling. At the moment, we try to focus on one single idea and one single model and try to perfect it and give it our heart and soul. And but what I want to say here is, when we are doing that as well, think about how do you share this knowledge with someone. If you can break this use case into multiple chunks, that's easier for you to debug, that's easier for you to share this sort of experience with others as well. So learning to is as simple as having a model registry, right? So it's just storing your training data, model stats. Yes, this is what Git does as well with versions, but now we are talking about horizontally as well. So we have one model, we have similar 5 models which are trying to compete with the production or the alpha model. How do you sort of compare them on horizontal basis as well? It gets easier once you start having a registry, and this sort of having a registry can build a foundation for you to compare the models as well. And there you go, the third learning, which is the most important that I've learned, which has given me the most impact with respect to how I compute different models and how I productionize them as well. This is left shift of feature store. So feature store, as we all know, is storing the features that we sort of either aggregate a couple of columns or write a huge algorithm just to go find out one feature or a characteristic of our data, right? So once, say, in our use case, we are consolidating or reducing 4 weeks of data into one single row. So that's a lot of computation. But if I just run a model through that and just forget about it, then it becomes very difficult for me to run the consecutive model. So I'm talking about challenger models. So there are 2 other models competing with the actual one. So if there are 2 other models competing with the actual one, then I'm going to take 3x the amount of time to compute all 3 models. Whereas when you store the features, when you compute the first model and then use the stored features to run it, then it takes like 10% of the time to compute the consecutive models. In our EV detection model, that's exactly what we saw as well. 92% of the time that was taken for the model to run was just to fetch the data and engineer the data, sort of. And this is when you got to work with data engineers who are really good at efficiently transforming data and working or consolidating data or making sure there's a pipeline that we data scientists should work with them so that we get a better outcome for what we want to achieve as well. And the last one is model comparison. And this is exactly what I was talking about. We compare models on different stats like false positives, false negatives, accuracy, if accuracy is important for this use case or if precision is important for this use case, and have these weights set up. So if accuracy sort of is more required than precision, then we gotta go with more weights for that. And this is model comparison. And applying what we have learned, I'm gonna call it Spider-Man across the Spider-Verse because that's exactly what is the future. And it's inevitable for us to work on different models. And we will have to work on different models and try to compare and try to make them make the best out of what we can. And these are the few things like feature store, automating the model comparison, and sort of comparing. How do you make sure you compare the models becomes more important as well. And that sort of leaves us with the 4 learnings that I've come here to talk about. And I often think that frugal solutions are the answer for sustainable or future ready. Sort of any questions, and that's it for me. Thank you.